This week we're going to talk about electric flux and Gauss's law. But before we do that, let's do this little exercise. I've got a box that's hiding a charge distribution, but I'm showing you what the electric field looks like at various points around the box. Pause the video and see if you can come up with a charge distribution that's inside the box that would produce this electric field. These electric field lines all look like they're radiating from one point in the center of the box. It appears that we could put one charge at the center of the box and it would produce this electric field. These four are all the same distance away, so the electric field vector would be the same length, the same strength electric field at each of those locations. And these four are a little farther away, so their electric field would be a little smaller due to the extra distance from the point charge. I think a point charge at the center of the box would be a good approximation of a charge distribution that would produce this electric field. Let's try this one now. I've indicated four electric field vectors around the box. See if you can figure out what kind of a charge distribution inside of the box would create that electric field. One possible solution is a positive and negative charge, two charges separated by a small distance. I'm going to draw in two charges, a negative on the left side and a positive on the right side. And I'll use blue to put the electric field line, so the field goes from the positive to the negative. It also goes out towards infinity in this direction, and it comes in from infinity to the negative charge in this direction. The field would make something like this. So let's look at the 4 points that were labeled. The one over here would point in this direction, and the one over here in this direction. That looks like that works pretty well. Any point that's on that line between the two charges has an electric field that points to the left. And that's what we get here. We're pretty close to those two charges, and the electric field points to the left here. And here we're much farther away, so the field is smaller, but it points to the left. So I think a charge distribution with two charges, a positive and a negative, would work in this case. Let's do one more. I think one possible charge distribution is a line of charge. So if we had a whole line of positive charges, they would produce an electric field that looks like this. As that line of charges becomes longer and longer and longer, the electric field lines become more and more parallel coming off the charge distribution. And when that line goes to infinity, the electric field lines all become parallel. As long as it has a finite length, we get these edge effects out here where the electric field starts to go in a different direction. But if we're near the center, if we stay near the center, the electric field lines are very close to parallel. The point of this exercise is that there's a relationship between the charge distribution and the electric field it's creating. And if we know something about the charge distribution, we can tell something about the electric field, and vice versa. If we know something about the electric field, that tells us something about the charge distribution. And that's important to understand for Gauss's law. Before we discuss Gauss's law, we need to introduce a term we call flux. Flux is basically a flow rate across an area, but it depends on a few different variables. So I like to use this analogy. Fishing in a river with a net. If we have a river, and I know in a real river the water flow is fastest at the center, and it tails off and gets slower near the banks of the river. But just to keep things simple, let's have our water flow be uniform across the whole river. So the same flow rate across the whole river. And you're going to put your fishing net in there. You want to catch a fish. You're going to put your net into the river. How are you going to do that? Are you going to put your net into the river like this? I think you're going to be hungry tonight, because none of the flow of the water penetrates the area, the surface area of the net. Here's the flow of water, and you've taken your net and put it in so that the water grazes across the surface without penetrating the net at all. Now you could turn your net a little bit, and you'd have a greater chance of catching a fish. And you could turn it a little bit more, and you'd have your greatest chance of catching a fish. So one variable is the orientation between our flow and our surface. Can you think of another variable that flux depends on? How about using a bigger net? If you put a bigger net in, you'd have a better chance of catching a fish than if you use a smaller net. The area of the net is another variable. And can you think of a third one? If you're a utility company and you own the dam at the top of the river, you can control the flow of water in that river. So the third variable is the flow of water. Now let's talk about electric flux. We'll use a small e there to indicate it's the electric flux, because in a few weeks we're going to be talking about magnetic flux also. But right now we're talking about the electric flux, the amount of electric field that penetrates a surface. And what would it depend on? It would depend on the strength of the electric field. That's like the flow rate of the water, right? The strength of the electric field. It would depend on the area of our surface. And it would depend on the orientation between the two. This is true if E is constant over the area. Now, why did I use a cosine theta there? Let's go back and look at our orientation here between the net and the river. Our area is a surface. How do we define a surface with a vector? Well, there's an infinite number of vectors within the surface. But if we pick a vector perpendicular to the surface, that pretty clearly defines the orientation of the surface. So that's what we do. We pick a vector, an area vector, that's perpendicular to the surface. So you can see that when the angle is 90 degrees, as in this case, between the area vector and the electric field, or in this case the water flow, we have a 90-degree difference between those two vectors. The surface is actually parallel to the flow of the water. That's why we use a cosine theta here. We would get 0 for the flux in that case with that orientation. But over here, we get our maximum flux. The area vector and the electric field vector, or in this case the flow rate of the water, are in the same direction. There's a 0-degree angle, and cosine of 0 is a maximum. It's 1, and that gives us our maximum flux. We can also write this as a dot product. and the area vector is normal to the surface or perpendicular to the surface that it's defining. This is true if the electric field is constant over the area, but the electric field might not be constant over the area. So in general, we would have to integrate. We would have to integrate the electric field over the area to get the flux. Let's do this little exercise. Find the flux through each surface and the net flux through the cube for a cube sitting in a uniform electric field. So let's number the surfaces. I'll call the one back there 1. And how about the face we'll call 2 and 3 and 4, and then 5 can be the top and 6 can be the bottom. So we've numbered all 6 sides of our cube. Find the flux through each of those 6 sides and the net flux through the cube. Now that you've done them, I'll go through and do them, and we'll see if we get the same answers. The flux through surface 1 is just going to be the electric field times the area times the cosine of the angle between them, because the electric field is constant over the area. It's uniform field, it's the same everywhere. So we have a constant electric field. So E times A times the cosine of the angle we get when we put their tails together. And we have to come up with a definition here, don't we? Because we have a surface sitting here, and we know the area vector is perpendicular to that surface. But does it point in this direction, or does it point in that direction? Well, our definition is that when we have a closed surface, and we have a closed surface here, what is a closed surface? A closed surface has an inside and an outside. So this cube is a closed surface. It has an inside and an outside. When we have a closed surface, the area vector points out from the enclosed volume, outward from the box. So it would not be this inner one. The area vector would be this one right here, pointing outward from the box. Side 3 would have an area vector that points in this direction. Side 5 would have one that points in that direction, and you get the idea. Maybe that's the information you needed. You can stop the video and go back and check your answers, and then you can come back and see what we get. So for side 1, I've got E times A times the cosine of 180 degrees. I've got negative EA. We're just going to call the surface of each side A and the electric field E. For surface 2, I've got the electric field times the area times the cosine of 90 degrees, because the area vector points outward from that surface and the electric field points that way, and we have a 90-degree bend between them. 0 for surface 2, and you can look at it and you can tell that none of the electric field lines are crossing that surface. None of them are penetrating the surface. They're just skimming right across the surface. None of them are going through the surface. They're parallel to the surface, so we have a flux of 0. For surface 3, we're going to have E times A times the cosine of 0 degrees. For surface 4, EA cosine 90 degrees is 0. And for surfaces 5 and 6, we also get that. Now, how about the net flux? Let's add it all up and see what we get. The net flux turns out to be 0. We have some positive flux on one side where the field is exiting the cube, and we have some negative flux on the other side where the field is entering the cube, and it nets out to 0. And that brings us to Gauss's law. Gauss's law links the flux, the integral of E dot dA, over a closed surface. That's what this little circle means on the integral sign. We're integrating over an entire enclosed surface, all the sides of an enclosed surface. The flux of E dot dA over an enclosed surface is proportional to the charge inside the surface. And of course, we like to have an equal sign there. So we need a proportionality constant, and it's 1 over epsilon naught. Let's think about our previous example real quick, and then we'll come back and talk about this some more. In the previous case, we just had a box sitting in an electric field, no charge inside. So Gauss's law would tell us if Q inside is 0, there's no charge inside the box, there has to be a net flux of 0, and that's what we got when we did the calculation. Epsilon naught is 8.85 times 10 to the minus 12, and it shows up a lot in our electrostatics equation. So we see epsilon naught a lot, and we have another constant called mu naught, which shows up in our magnetic equations you'll see later on. Gauss's law links the electric field to the charge inside of our surface. That means that we can use it in certain situations to find the electric field if we know something about the charge distribution. Right now, we have 2 techniques for finding the electric field. One is the technique we learned last week. We use the electric field is the integral of k dq over r squared. Integrate over the charge. And now we have a second technique where we'll use Gauss's law. The integral over a closed surface of E dot dA is equal to Q inside of that surface over a constant. So we have to look and see how do we use Gauss's law to get the electric field. Let's do that now. Let's start with something we know. We know the electric field near a point charge is kq over r squared. So let's see if we can use Gauss's law to get the same result. A point charge fills the space around it with an electric field that radiates radially outward from the point charge. And the key to using Gauss's law is that we look for certain symmetries in our problem. Let's go back and take a look at our 2 methods for finding the electric field. There's an integral here where we're integrating over the charge distribution. There's an integral here where we're integrating over the area around some enclosed shape. We want to pick whichever one is easier to do. Sometimes these integrals are very hard. Sometimes they're a little simpler. We want to pick the integral that's the easiest to do. When is Gauss's law an easy integral? Well, unfortunately, there's only a few cases. But in those few cases, it's really easy. And so that's why we're spending time learning it now. One of those cases is when we have spherical symmetry, like we do with a point charge. The point charge is radiating its electric field outward radially in all directions, so we have spherical symmetry. If we go a distance r away from that point charge, it doesn't matter if we're over here, or down here, or over there. The electric field is the same because we have spherical symmetry. That means we can draw a sphere around our point charge, an imaginary sphere, and everywhere on the surface of that sphere, the electric field would be the same. Not only would it have the same magnitude, but the electric field would point radially outward, so it would be perpendicular to this imaginary surface that I drew. We call that imaginary surface a Gaussian surface. And how big do I make my Gaussian surface? I make it where I want to know what the electric field is. So I don't really want to know at a specific place. I just want to know at some arbitrary distance r away from my point charge what's the electric field. So I'm going to call this distance little r, some arbitrary value that's a variable. So the integral of E dot dA over that closed surface, that red sphere that I drew there, that Gaussian surface, is going to equal the charge inside over our constant epsilon naught. The electric field is constant everywhere on that sphere, that's what we just said, and it's normal to the surface. So the dot product, this is going to be E times A times cosine theta, and the electric field is constant, and the area of that sphere just depends on the r, and the cosine of 0 degrees is 1 because the area vector points outward and the electric field vector points outward. We have a 0 degree angle when we put the tails of those two vectors together. So this just becomes E times A on the left side of our equation. How much charge is inside of our imaginary surface, our Gaussian surface? Well, let's just call it Q. And we have this constant epsilon naught here. The electric field is Q over A epsilon naught. What is the area? The area is our Gaussian sphere. So in this case, it's a sphere. Sometimes our Gaussian shape is different than a sphere, and then you use the appropriate area there. But in this case, because we're dealing with spherical symmetry, we chose a sphere for our Gaussian surface. We need to match the symmetry of the problem. If I put a cube around this, then doing the integral of E dot dA over a cube, right, the surface of a cube with the electric field changing direction and changing magnitude, that would be a very difficult integral to do. But if I choose a sphere, and because I have spherical symmetry, then this integral becomes trivial. Everything is a constant, the cosine of theta is just 1, and it becomes E times the area. So I have here Q, the area of a sphere, and epsilon naught. I'm just going to rearrange this a little bit. 1 over 4 pi epsilon naught. Those are all my constants. I have the charge, and I have 1 over r squared dependence. Now, 1 over 4 pi epsilon naught is actually our constant k that we use in our electrostatics equations. So this is k q over r squared.